Welcome, everyone. Good afternoon. It's my great pleasure to introduce Dr. Chris Depner from the University of Utah. Chris got his master's at Montana State University with Mary Miles, and then transitioned to Oregon State University to get his Ph.D., where he was really looking at nutritional aspects of health. And I think when I met Chris, he was really into fish oil. Um, and because that was kind of the big dietary trend at the time. And you were the first person to say, I think, it doesn't do anything, or it doesn't do as much as people make it seem like it's doing. And so it was a great relief to me to find out that I didn't have to be slurping down fish oil all the time. I met Chris when he started a postdoc at the University of Colorado in Boulder with Ken Wright. And he was kind of coming in as I was going out. So I think we overlapped for a year-ish. And Chris really brought a new nutritional perspective to the lab and really opened up the lab to taking an omics approach to many different ways that we look at health. And so today I'm really excited to hear about some of his newer work looking at sleep extension and circadian-based interventions. And I will turn it over to Chris. And he has mentioned that he is willing to take questions at any point during the talk. I'll have a couple pause points, and I will be monitoring the chat. But Chris, it's all you.
Awesome. Thanks so much. I'm super happy to share some of my work today. And yeah, funny introduction. I don't want to derail us too much, but my older brother, when I was like, I don't know, 6 or 7, broke my nose and I have a deviated septum. And I swear that fish oil is improving my sense of smell these days. And I got on a kick earlier this year of eating sardines for lunch, and I overdid it a little bit too much, and I ended up giving myself gout from all the purines in the sardines. So that's a firsthand lesson to not maybe take it to the extreme of sardines for lunch every day. But we'll move on. So yeah, I'm definitely happy if anyone wants to interrupt at any point. Feel free to do so. I have like 2 really broad topics to talk about today. I'm half predicting I won't even get to number 2, and that is the night shift work and cardiometabolic risk that I've been working on with Andrew for seemingly years now, and a lot of our omics analyses. And we just got a new paper on that domain accepted in the Journal of Biological Rhythms. So that should be coming out in the next month. And assuming I don't get to it today, and if you're really interested in it, go look at our new paper and it's all there. So I'm mainly going to talk about some sleep extension and circadian-based interventions that we've been working on over the past couple of years in the lab here. And I want to set the stage a little bit for kind of our initial motivation to do these studies and talk about some of the lessons we've learned along the way. So to get started, as far as sleep and risk of diabetes, this is a compilation of a couple of different review papers showing traditional risk factors for diabetes, namely type 2 diabetes, and then some of the more thought about sleep risk factors, and those are in blue. And you can see here, let me pull up my, okay. Obstructive sleep apnea is among the top for the sleep-related risk factors. And then a little bit lower is difficulty maintaining sleep and a sleep duration less than 5 hours per night, which this is important when we're looking at some of my data that, this here is specifically less than 5 hours per night. And one other important thing is that overweight is at the top, which I think that will actually come into play kind of at the end with some of the data I'm summarizing. But the take home is we think these sleep factors are important, and they're certainly based on relative risk in kind of the same range as what we think about for some of the more traditional risk factors that have been maybe a larger focus historically. And I want to go all the way back. I found this study, I don't remember, several years ago. It was published back in 1969. Excuse me. And it's called Metabolic Reflections of Sleep Deprivation. And this was, I forget, like 2 or 3 days of a total sleep deprivation protocol. And they ultimately did an oral glucose tolerance test, although they didn't call it an oral glucose tolerance test in the paper. It was just this glycemic excursion, I think. And this is the data. So the top curve with the black circles is the glucose response to this oral glucose tolerance test after the sleep deprivation protocol. And then the open circles with the dashed line is that same response, but after adequate sleep. So that was before the sleep deprivation occurred. And you can see here very clearly there's an impairment in this glucose homeostasis that's occurring with the sleep deprivation. And so, I like to point this one out because it's at least one of the earliest papers I know of in kind of modern published literature. I'll go back. Hopefully that doesn't keep happening, but if it does, okay. And so that was all the way back in 1969, showing that we know that there is at least this acute impairment in glucose metabolism with this total sleep deprivation. Following up on that, in 1999 was when Ev Van Cotter from University of Chicago published one of her sort of seminal papers in the Lancet showing, I'm not going to show the data, but it was 6 nights of 4 hours time in bed per night of an experimental sleep restriction protocol. And they used a more sophisticated test, the intravenous glucose tolerance test, and they found similar findings where there was this impairment after sleep restriction. And they did see a recovery back to baseline after they did 12 hours time in bed for 6 nights. So they basically did a one-to-one, at least time in bed replacement for that recovery sleep. And they did see that these participants, this was all men, they did recover after that sleep loss. Again, I just want to highlight this was a 4-hour time in bed sleep opportunity. So it was still quite severe sleep restriction. And again, I'm highlighting that because it's, I just want to contrast it to what we're kind of finding with some of our more free living studies that we have going on. And so to sort of fully set the stage for our initial motivation, I need to go back and explain the study that was one of the first ones I did back in Ken Wright's lab. And this was published back in 2015, so 11 years ago now. So it's kind of an old study at this point. It was a crossover design in lab experimental sleep restriction. This is condition order A. So participants came into the lab. They had 3 days of adequate sort of habitual sleep that was considered baseline. And then on day 3, you can see we kept them in dim light, which is indicated by the gray shading there. And that allowed us to do 24-hour sampling for melatonin to track the timing of their central clock. So we did 24-hour melatonin curves. And this was a setup, which I know at least some of you are familiar with, where the participant was hooked up to an IV with tubing that runs out of the room. And that way we can do overnight sampling while the participant still has their sleep opportunity. Following that, in this particular condition order A, participants had 5 days of maintaining that 9 hours time in bed, but they had free access to food, so ad libitum food intake during wakefulness, whereas food intake was controlled to keep them in energy balance for the first 3 days. At the end of that condition, then we measured circadian timing again, and then in this case, they did finish it up with the 5 days of 5 hours time in bed. And we kept their midpoint of sleep centered here. So they had basically a restriction with a later bedtime and an earlier wake time, and measured dim light melatonin onset again at the end of that. You can see in each condition, we measured insulin sensitivity using the oral glucose tolerance test. And then it was a crossover design, randomized. So the other half of the participants completed the 5-hour sleep restriction condition first, followed by the 9-hour condition. So remember, at baseline in A and B, energy intake was controlled, and then they had ad libitum access to food for the 9-hour and 5-hour conditions, regardless of order. And so this is definitely published data. This is the dim light melatonin onset and offset data. So the up triangles are melatonin onset, and then you can see the sleep episodes are indicated by the rectangles in the middle, and then dim light melatonin offset by the down facing triangles. And so, this is a very healthy young participants. And so you can see here, as far as their sleep timing was concerned, essentially melatonin onset was occurring before their bedtime at baseline, and then they were waking up just before melatonin offset. That's also at baseline. This is during the 9-hour control condition where they still had the same sleep opportunity, but they had free access to food, and they were eating a bit more during this 9-hour condition. Still, we see no meaningful changes in the timing of melatonin onset or offset here. And this is a 5-hour insufficient sleep condition. I should say, just to be clear, other than the 24 hours where they were in dim light and we were measuring melatonin for onset and offset, participants basically, there's a window in this room and they had normal room lighting, so they were exposed to, we'll just say, 200 to 300 lux of light. So it certainly wasn't dim lighting throughout most of the protocol. So this is what happened during the 5-hour condition. There was a significant delay in dim light melatonin onset. You can see their sleep opportunity was shortened, still occurring after onset. However, there was no shift in melatonin offset in the morning, but that did create this wider phase angle between wake time and melatonin offset. And so we looked at that a little bit further. Okay, I'll come to that in a second. I want to show you the insulin sensitivity data first. This is by the oral glucose tolerance test. This is similar to prior data from many different labs and many different groups that had studied this up to this point, where we see an impairment in insulin sensitivity on that oral glucose tolerance test during or following sleep restriction relative to the two adequate sleep conditions. We did the intravenous glucose tolerance test in this study as well and saw a similar magnitude of impairment during insufficient sleep. I want to put this also in context, mainly when I'm talking about future sleep extension studies that we have going on. One of the sort of thresholds that has been proposed for this Matsuda index from the oral glucose tolerance test is a level of 4.3 for defining impaired insulin sensitivity at sort of a clinical level. Certainly, like, this isn't like necessarily directly related to like progression to type 2 diabetes, but it's a threshold that's been proposed as maybe a clinically meaningful threshold. So I just kind of want to point out that 4.3 threshold, and we'll come back to it a couple of times. So ultimately is what we did in our paper that was a bit new, that was again published back in 2015, was we looked at the association between that phase angle between wake time and melatonin offset. So that was the one that changed, and this change in insulin sensitivity. And ultimately we found that people with a wider phase angle, so basically a longer duration from when they woke up to when melatonin offset was occurring, that was associated with worse insulin sensitivity. And I adapted this figure from our published paper because I think it more clearly shows the three different conditions. And you can certainly see here in red is that insufficient sleep, 5-hour sleep restriction condition. And you can see that on average, there are the participants, or that's when the participants had the widest phase angles and the lowest levels of insulin sensitivity. Again, I want to point out that these were actually pretty wide phase angles. You can see like most of these participants in the red, the insufficient sleep, were falling between this like 2.5 to 7.5 hour time range for the phase angle. So this is then unpublished from this study. Remember, they had free access to food, and one of the things that was quantified was post-dinner snacks, which is basically total calories consumed between the end of dinner and then bedtime. And this is data that Ken Wright had already published as far as there was an increase in post-dinner snacks with that sleep restriction. And as what I looked at here was that same association. So in this case, the association is between post-dinner snacks and insulin sensitivity. And it turns out there's a similar association in this study with this like post-dinner snack, I'm just going to call it nighttime food intake, and lower levels of insulin sensitivity. And I think this would be consistent with some other data that shows that, you know, there's potential adverse health consequences of a lot of late night food intake. And this sort of raised an interesting hypothesis for us that we're still trying to work out, but like really, because the study wasn't designed to disentangle this, like, is it the sleep loss itself that's really driving the impairment in insulin sensitivity? And both these sort of phase angles and nighttime food intake are kind of co-occurring, or are these things, the phase angle and the post-dinner snacks, actually, they're happening from the insufficient sleep, but they're actually driving the impairments in insulin sensitivity? So, like I said, this study wasn't designed to disentangle all these different factors, but we certainly see all these things happening, which has raised some interesting questions for us as to like what truly might be going on in sort of free living environments where people are getting insufficient sleep, and maybe what's driving what. And we think this is important because if we're trying to design interventions, what the targets of the interventions might be is important. So that's kind of how we're thinking about this. So that's kind of the motivation behind some of these studies that I'm going to talk about today. The first one is free living sleep extension intervention. And I'm calling this the RADS study, which isn't too important, but I will refer to it as that. And then the second one is a very preliminary study that we still have some data collection ongoing for. And we were kind of exploring the idea of doing a circadian-based intervention in people with insufficient sleep to see if we could modulate that phase angle and kind of explore a little bit more what might be going on with that phase angle under free living conditions. So first, I want to talk about the sleep extension study. We did have our first paper on this recently published earlier this year. It's in Sleep Advances, and this was headed up really by two PhD students in my lab. Misha, she actually did her undergraduate back at Colorado, so I have worked with her for quite a while. She's a postdoc now at Colorado State University, and then Audrey's a current PhD student in the lab. So there are some more details in this paper if you're interested in looking it up. So for this study, we were trying to kind of just move one step beyond the laboratory controlled trial. So we're still recruiting relatively healthy young adults, but they at least reported habitual insufficient sleep. So in this case, we set a threshold of a self-reported level of less than 6.5 hours per night. And we had asked about that over the prior 6 months. For BMI, they were in sort of the normal healthy range, and they reported no medical, psychiatric, or sleep disorders, and they hadn't worked shift work in the prior year. And we started this study. Our first participant was enrolled in the end of February 2020. We had initially aimed for 40 participants, and pretty much as soon as we got that first participant enrolled, all human subjects research was shut down due to COVID. So there was a bit of a delay on this, but ultimately we did get 38 participants enrolled in the study. So we did a pretty good job with it. This is the protocol. So we did 2 weeks. You can see day is going down the y-axis, and then relative clock hours on the x-axis in this. So for the first 2 weeks, we monitored sleep with primarily wrist actigraphy in the home environment, and participants were just instructed to maintain their habitual sleep schedules during that time frame. We brought them into the lab for a 24-hour, not quite a 24-hour, but an overnight laboratory assessment. Our initial plan was to have them in dim light and capture dim light melatonin onset and offset, and then also do an oral glucose tolerance test during this time frame. Ultimately, we did capture dim light melatonin onset with some of the participants, but due to COVID restrictions, we ended up having to kind of nix the vast majority of that for most people. So we just were unable to actually collect samples for them because they weren't coming into the lab early enough. So ultimately, we really just have to focus on the offset in this particular analysis, but we did get the oral glucose tolerance test on most participants. After that baseline assessment, we worked with the participants to set target bed and wake times to increase their time in bed, noting that these were people with like low depression scores, low anxiety, no sleep disorders, specifically insomnia. And so these were people, by getting them to increase their time in bed, and I'll show you, we were able to get them to increase their sleep duration. And so we did that for 4 weeks and monitored that again in their home environment. And then they came back into the lab at the end of that for the same in-lab assessments. On a subset of these participants, 16, we were able to use doubly labeled water to assess in the free living environment what their total daily energy expenditure was over 2-week time frame. So that was the 2 weeks of baseline and then the final 2 weeks of the intervention. And I'll share some of that data with you today. We also used the ActivePal device, which is a thigh-worn device to monitor physical activity and sedentary time. And I do have some other data during the final week of each baseline and sleep extension. We had them wear the Dream headband, which has dry EEG electrodes. It has a couple frontal and a couple occipital electrodes. So we did get some estimates of sleep staging from that Dream headband device, which is published in our paper, and I'll share that with you as well. So this is the total sleep time data derived from wrist actigraphy. We reported it in the paper on weekdays and weekends, and I realized there's kind of a lot going on statistically in this figure. The first thing to note is for each segment, there were no statistical differences between the weekdays and the weekends. So for these particular participants, we really didn't see major differences in total sleep time across weekdays and weekends. We certainly see them on average just below 5.5 hours of sleep during baseline. And then essentially these are the first 2 weeks of sleep extension. Again, this is going to be weekday, weekend. And then these are the final 2 weeks of sleep extension, weekday, weekend. And ultimately we saw a pretty rapid and consistent increase in sleep duration across the 4 weeks of sleep extension. It was about it was just under 50 minutes of total sleep time increased. So the time in bed increased by just over an hour. And we saw that happened actually really quite rapidly during the first 2 weeks, and it was maintained throughout the intervention. And again, we saw that occurring, that extension was happening during weekdays and weekends similarly. So it wasn't just like they were catching up on the weekends or something like that. So we were pretty happy with this. It was our first kind of attempt at doing this sleep extension type of an intervention. And the fact that we got just over 45 minutes of total sleep time increase was encouraging. Participants ultimately did this for the most part by having an earlier bedtime. So this is all the individual participant data for bedtime. And you can see on average bedtime increased shifted earlier by about 52 minutes. There were a couple of participants with later bedtimes, but on average, you can see that's how participants were mainly increasing their time in bed. And then as far as wake time goes, the average was a 9-minute change in wake time, which was not statistically significant. But you can see, looking at the individual data, there's a number of participants that actually had earlier wake times and then a number that also had later wake times. And so, certainly some participants did start sleeping in a little bit later during this protocol. And with kind of the changes across the board here, obviously the average change was not significant, but it's worth noting that certainly some people also modulated their wake time. These are the data from the Dream headband. And it basically, we use the auto scoring algorithm. I don't know if any of you who are doing sleep research ever used the Dream. You can get the raw data from it. We looked at that. It's pretty noisy. We see a lot of artifact in it. So we, decided to ultimately just go with the sort of validated Dream algorithm that they have. The Dream device isn't really available for research anymore anyhow, but it was cool to be able to use it. Ultimately, is what we did see is an increase in stage 1, stage 2, and REM sleep as the primary changes in sleep stages. And for stage 3 sleep, we didn't see any significant changes. Again, this was during the final week of sleep extension, so perhaps there could have been some changes occurring earlier in the intervention, but we didn't capture it during that time. We saw a similar increase in total sleep time from the Dream headband. It was slightly higher. I think it was closer to an hour, but I think it's on par, generally speaking, with what we saw with actigraphy. And then there was the slight increase in wakefulness after sleep onset, which I don't think is too surprising because we were getting them to really increase their time in bed by an hour to an hour and a half. Really quickly, I don't want to go into it in too much detail, but we also did the Pittsburgh Sleep Quality Index and the Epworth Sleepiness Scale, and we did see significant improvements in both of these. We don't have a control group. This was still really a pilot study. So, some of this could be the fact that they were in a sleep study. They were tracking their sleep. So, we don't have that control group comparison, but I will say, the improvement in the Epworth Sleepiness Scale going from an 8 to a 3 is really, that's quite a big improvement. So for insulin sensitivity, so the rest of the sleep data is in that published paper. So again, you can definitely look that up if you have any detailed questions, or you can obviously ask me too. For insulin sensitivity, at baseline, the average was about 7. So remember that 4.3 threshold. Our participants here, even though they were getting less than the recommended 7 hours of sleep per night, their insulin sensitivity was, for all practical purposes, most of them were in what would very much be considered the healthy range here. And during sleep extension, that was maintained. So that's not overly surprising in that if they were already healthy, getting more sleep is unlikely to make you more healthy. Like, there's not really much room for improvement. I will say I was a little bit surprised. I kind of expected at least more of the participants at baseline with those lower levels of sleep to have some level of impairment just based on all of the experimental sleep restriction data that had been published previously. So this was a little bit higher than I anticipated, but there was no change here. So we didn't see any meaningful changes. And again, that's the 4.3 threshold. We do see some participants below that, but on average, our group was well above that during both baseline and sleep extension. I will say we've looked at some correlational analyses, and we don't have a big range of sleep duration here. And certainly when we look at if total sleep time is associated with insulin sensitivity, with kind of this limited data set, we don't see a correlation there, which is probably not surprising given the data set that we're looking at. So I just want to take this back to the in-lab sleep restriction study that I had published previously with Ken Wright. And again, I'm just going to highlight that 4.3 range. So the data I just showed you from our free living experiment is here on the left. And on the right is the experimental sleep restriction in the laboratory. And one thing to note that's very clear is the variability and kind of the range of the data is much tighter during the experimental sleep restriction in the lab. This is during adequate sleep, and you can see virtually all participants are above that 4.3 threshold, whereas during sleep restriction, you can see the average was about right at that 4.3, and about half of the participants actually dropped below that 4.3. So that was 5 days, 5 hours time in bed. We did see this significant impairment, and that was at a level, again, we'll just say the average here, 5 hours time in bed in the lab. That average was far below the average we see in these free living participants who are getting about 5.5 hours of sleep. So again, based on these initial data, I had expected our baseline data to show some more impairment. But this is what it is, and this is why we do the real world studies. So that's that comparison. I want to also show you the melatonin timing data. And again, this is similar to the prior data I showed you as far as how it's structured with the sleep opportunity in the middle, and then offset indicated by the downward facing arrows. We did not, so for melatonin offset, there actually was a little bit of a delay that was statistically significant going from baseline to sleep extension. We haven't looked at light exposure data, so I'm not totally sure like what their light exposure looked like. We could look at that from their wrist actigraphy data. They wore the Philips watches during the study. I know there's potential issues with like the watches being covered with sleeves and stuff like that, but we could at least look at that morning light exposure and see if there's any signal of anything potentially happening there. But nonetheless, we did see a little bit of a delay in melatonin offset. However, when we looked at the phase angle between the two, the baseline and sleep extension, that was not significant. So we didn't see a significant change in this phase angle. Something else I want to point out is this phase angle is in the neighborhood of about 2 hours. And remember, I noted in the experimental laboratory sleep restriction study, what we were seeing with sleep restriction was a phase angle in the neighborhood of about 2.5 to 7.5 hours. So that phase angle during experimental sleep restriction that was associated with impaired insulin sensitivity was far wider than what we see in these free living adults in this sort of more free living paradigm that we've studied here. So again, we're about 2 hours here, 2.5 to 7.5 hours in the lab. So the magnitude of difference is really, I would say, striking. So we did also try to see, I'm not showing it to you, we tried to see if this particular phase angle was associated with insulin sensitivity in the study. And in this, again, in this set of participants, we don't see that association holding true. So now I want to shift to the physical activity data. This is going to be a separate publication, and this data is very close to being submitted. So hopefully it'll probably be submitted within the next month, I would say. So hopefully by 2026, it'll be published.
Hey, Chris, we have one question about the sleep, and I thought it might be good to touch
totally.
on it. So Matt Butler asked, in the sleep extension, the total sleep time is only at 6.5 hours. What is preventing longer sleep?
Oh, that's a good question. We tried, I'll go back to it just so you can see. Yeah, it's about 6.5. We actually tried to get them up to a 2-hour time in bed increase. And I think had we achieved that 2 hours of time in bed increase, we probably would have gotten more people to like that 7-hour recommended threshold. That's a really good question. A lot of people have asked, like what were people doing, with increasing their time in bed? What were they losing or replacing? And honestly, we didn't ask them about that. So I wish we would have. We worked with people, we assigned them a time in bed that would increase the schedule that would increase their time in bed by 2 hours. And honestly, most people were able to increase by an hour to an hour and a half. So I would just naturally, I'm totally guessing, but most people did have to get up in the morning for class or for work or whatever. So there wasn't as much wiggle room for most people in the morning. And I think, I can imagine it was just a little bit challenging for people to actually get into bed and sleep like 2 hours earlier than normal. But we didn't specifically ask them about that. But, we targeted that 2 hours time in bed increase, and this is what we achieved. So I do think it would probably be pretty challenging to get them to increase by significantly more than this, especially if you start thinking about longer interventions.
And I had a question. When you go back to the Matsuda, if you go to the Matsuda data, are the people that are on the lower tail, did they change, or were they the same people in the lower tail?
They were, I don't have it specifically, but we have looked at that, and most of the people like on kind of this lower end, they kind of maintained that same lower end, which does, well, I am going to get into this a little bit, but it does make you wonder, like, if it's not sleep duration, like maybe what else why are these people consistently low? Because there's quite a range here, the low end to the high end, like that's from potentially going to diabetes to extremely healthy. So,
and I missed the inclusion, your body fat criteria?
Normal body mass index, so less than 25.
Okay, and then last thing, so I wonder if it's just like a slow wave sleep effect, like because you have it conserved across both in like the Tasali paper, and I don't remember in the current biology paper, did we look at slow wave sleep with I know we looked at the phase angle of, but because it was curtailed 5 hours on each side, so maybe doing that in a acute way makes a REM rebound, which eats into the slow wave sleep. So maybe there's a decrease, I don't know.
There definitely, and there's enough range. I'm looking at the slow wave sleep now. There's enough range in the slow wave sleep that we could look at that. And honestly, we haven't. And we haven't published the Matsuda data yet, so we'll add that to the paper that will be forthcoming. It's at least worth exploring because yeah, the older Tasali study showed, and there's another study too where they show like the impairment of slow wave sleep is associated with decreased insulin sensitivity. Yeah, we'll definitely look at that. I can't say, but we'll look at it. That's a really great
Yeah,
idea.
I'm just wondering if it's like a protocol artifact because of the way it was
Yeah,
curtailed in the lab versus the way it's been extended in real world, as people are adding more sleep onto the front end, but their offset is basically the same, right?
exactly. Yeah, exactly.
I'm curious if
And
you extended it on both ends, like if that would have a different effect than just.
totally. Yeah, it very well could. And from that in-lab study from Ken's lab, we obviously have the PSG data. I don't recall. We definitely have never published, and I don't know if we ever did look at those potential correlations with sleep staging and the insulin sensitivity. So that definitely, it's an interesting area to explore for sure, because I think there's some possibility there.
Yeah.
Cool.
Okay, thanks.
Yeah, of course. Thank you. Um, let's see. Okay, so for some of the physical activity data, okay, this was sedentary time, again from the active file device, which is on the thigh. So it's typically considered a more accurate device as far as measuring physical activity and sedentary time compared to a wrist-worn device. And we did see a significant decrease in sedentary time. It's about an hour. I am sorry, I realize this is the total sleep time is in hours, and this is presented in minutes. So it's a little bit hard, but it was about an hour decrease in sedentary time with sleep extension. And to look at this a little bit more, we plotted the accumulation of sedentary time across the day in baseline and sleep extension for basically starting from wake time moving forward. And so T0 here is essentially wake time. And then the average bedtime for baseline and sleep extension are indicated in the dashed lines. So remember, sleep extension, they're getting insufficient sleep, and that's where their bedtime was later. So that's the yellow here. And then the sleep extension bedtime was earlier, and that's the blue dashed line here. So that's where they're going to bed earlier. So you can see the rate of accumulation across the day is really the same between both segments of the study. And you can see the drop off in sedentary time is happening right around bedtime. So essentially, is what it looks like is happening here is they're replacing, which it's not super surprising, but it's kind of cool to see. They're replacing about an hour of sedentary time at the end of their day with an hour of time in bed, which, you know, in this case, most of our participants, like they're relatively healthy. They have a healthy Matsuda index. But it does raise a question of, is an hour of time in bed, and if you're actually sleeping during that, like if you're getting 45 minutes to an hour more of sleep and you're replacing that with sedentary, or replacing sedentary time with that, are there potential health benefits to that? It's an interesting question that, you know, I don't think we can totally answer in this study. And this is just to show this a little bit more, that the total sleep time throughout the study was strongly associated with sedentary time, where we see higher sleep was associated with less sedentary time. So it's kind of an interesting exploratory analysis. As far as light physical activity, we didn't see any significant changes between the two conditions. And same with moderate to vigorous physical activity, we didn't see any changes. And you know, one of the questions that has been kind of posed, especially when you go to like the ACS, American College of Sports Medicine conferences, or talk to some of the physical activity folks, they always kind of wonder if there's like potential changes with spontaneous movement across the day and sedentary time with insufficient sleep and adequate sleep, and what might be going on there. So that was our motivation to look at this. I'll say with the MVPA that most of the participants were getting more than 30 minutes per day. So we didn't specifically screen, for moderate to vigorous physical activity in the eligibility criteria. But we did ask participants just kind of habitually what their activity levels were. and most of them reported less physical activity than what they were getting by quantifying it on this device. And a lot of this activity was accumulated in small bouts, is what I can say. It didn't look like they were necessarily doing like a lot of big exercise sessions across the day. So that's kind of our interpretation there. So it's what we mainly see is this reduction in sedentary time. And then for the doubly labeled water data, where we're able to quantify average energy expenditure, total daily energy expenditure over a 2-week time frame. This is the energy expenditure at baseline and sleep extension. As far as quantifying free living energy expenditure, the doubly labeled water method is kind of the gold standard way of doing that. But it's still not as accurate as like a whole room calorimeter, for example. So there is going to be a little bit more variability in this data. But overall, the averages were almost superimposed on each other, and there's definitely no sign of a change in energy expenditure with the sleep extension intervention. And then with having the energy expenditure data, we're able to back calculate energy intake. I'm not going to go into it in detail, but if any of you are familiar with the Ezra Tasali sleep extension study in JAMA Internal Medicine published a couple of years ago, if you calculate changes in body composition, you can estimate basically like how many calories were gained or lost on the person's body. And if you know their energy expenditure over that same time frame, you can calculate energy intake. So this is the calculated energy intake data. And that also did not change between baseline and sleep extension. And again, these were healthy participants, normal body mass index, so healthy weight. So they didn't really have weight to lose. And I mean, I guess it's good to see that they're not gaining weight or eating more during sleep extension. We wouldn't necessarily expect that, but so no like really meaningful changes here. The Ezra Tasali study did show a reduction in food intake with sleep extension. That was participants who were overweight. So certainly there might be a difference in response here if we're thinking about like people with overweight or obesity versus lean participants like were in my study. So to kind of summarize that initial data, we did a 4-week sleep extension. We got people to increase their time in bed by about 45 minutes. Focused on increasing their time in bed. On average, insulin sensitivity was in the healthy range throughout the study, and that was despite participants having about 5.5 hours of sleep during baseline. On average, they were achieving the recommended level of moderate to vigorous physical activity. So they were, again, a relatively healthy population. And we're kind of following up on this now. We have an 8-week randomized controlled trial, sleep extension intervention. It's people with obesity and insufficient sleep, so they're definitely higher risk. And their insulin sensitivity is for sure lower at baseline. So that's ongoing. And so I'll be very curious what we find there with a longer sleep extension trial and a higher risk population. And so with that, I'm just looking at the time. I'll try to go through this next one quickly and save some time for more questions. The goal of this circadian intervention was really the notion from that laboratory trial that when we did experimental sleep restriction, we saw that wider phase angle, and that was associated with impaired insulin sensitivity. So there's kind of 2 key questions here. Like under free living conditions, adults with habitual insufficient sleep, what's that phase angle between wake time and melatonin offset? Do we see that, is that similar to what we see in the lab, or is it different? And then if we try to modulate that, thinking about lighting interventions, can we modulate that at all in the free living environment? So that was kind of the 2 key questions for this study. In this case, we recruited participants 18 to 45 years of age, still getting insufficient sleep, so less than that 6.5 hours per night. For BMI, we recruited people who were in the overweight to obese categories, and the average is 29, so they're just under that threshold for obesity. No psychiatric or sleep disorders. In this case, their apnea-hypopnea index is 5.0. we have a threshold. If they're 15 or over in the study, we exclude them, but we're going up to that 15 level. No shift work in the prior year, and this is definitely a pilot study, and we currently have 26 out of 28 participants. So for this protocol, again, it's mainly an at-home protocol. For days 1 through 6 at home, we track their sleep with wrist actigraphy. They come into the lab. They do, on day 7, an oral glucose tolerance test, and then we capture their dim light melatonin onset and offset in the lab for circadian timing. Then we go through 8-week intervention. We're not asking them to change their sleep in any way. We're really not guiding them anything specifically about their sleep during the intervention segment. And then at the end of the intervention segment, we repeat the same measures again. And this is a randomized control trial. So there's an intervention group and a control group. In the control group, during the intervention segment, which is 8 weeks, we're basically just giving them healthy lifestyle recommendations. These are really basic. They're modeled after the diabetes prevention program. It's not nearly as intensive as that, though, so it's very basic lifestyle guidelines. And then for the circadian intervention group, in the evening, we're having them wear these glasses, which we've measured those with a light meter. And if you're wearing them, they do block virtually all blue light, and they're really quite dark glasses. They block like 90% of all light coming in, and we've measured that like with a light box that's about 1,000 lux, and these then filter that down from about like 2 feet away. It filters that down to like 50 lux. So they definitely block out a lot of light, but you can still go about your activities with that. And then in the mornings, we have them for 1 hour when they wake up, wear these light therapy glasses, and then we do have light boxes that we give them, but most people really in the morning, they're moving around their house. So their ability to like sit and look at a light box is pretty limited. So that's why we're using these light therapy glasses. And they reflect about 1,000 lux of light into your eyes. So this is the melatonin data. This is at baseline in both of the groups. It's labeled a little bit funky. Actually, sorry, I take it back. This is baseline in the control group, and then the intervention segment in the control group. So this is the group that's just getting lifestyle recommendations. And there's just a time I'll just focus mainly on the interval here between wake time and offset. And you can see that that's, again, about 2 hours is what we're finding here, which is far less than what we're seeing in the in-laboratory study. And we do see this wider phase angle between melatonin onset and bedtime. So that's kind of where maybe there could be some misalignment happening. And then this is the experimental intervention group. We see a similar sort of phase angle with no significant changes between baseline and wake time and offset, and that remained consistent between the baseline and the experimental segment. We are seeing a trend right now. This is about 15 participants of data that we've analyzed. There's this trend for an earlier dim light melatonin onset, which is interesting because we are having them wear those glasses at nighttime, which could potentially maybe prevent some of that light that could be delaying them at night. So we'll have to see if that is maintained. The between condition analyses or between group analyses are not significant. Although we do see when we're looking at the duration from onset to offset, right now that is getting a little bit longer at the end of the experimental group, at the end of the intervention. I'm not totally sure what to make of this, and also it's very preliminary. It's not all of our participants, so I'm not, I guess, making too much of this right now. But if that does turn out to hold true, have to think about carefully like what that actually means. Their total sleep time, I'm just looking at my watch. Their total sleep time is still in the insufficient sleep range. You can see a couple of participants did end up above that 7 range, but ultimately they're about 5.5 hours on average. And there's certainly no hint. I mean, we don't have a lot of power here, but there's no hint with the data we do have that there's like any spontaneous changes in their sleep happening. We were a little bit curious if, if this intervention did actually shift their timing, their circadian timing around a little bit, would that cause any changes in their sleep? I mean, with our current data, that's definitely not happening. But this is definitely a pilot study, so just keep that in mind. As far as insulin sensitivity goes, remember these are people who are getting insufficient sleep, but they do have overweight or obesity, and there's no significant changes in their insulin sensitivity, but they're all, for the most part, very well below that 4.3 threshold on Matsuda index with the OGTT. So this has raised some interesting questions, and we're kind of doing some comparisons that I'll share with you in just a second between the two studies, because there is such this difference in Matsuda index and what might be driving that. So this is between the two studies. So this is baseline data in the sleep extension study on the left, which I've already shared with you. This is Matsuda index and the circadian study I just shared with you. And that's that 4.3 threshold. Unsurprisingly, these are definitely significantly different from each other. And so we've kind of started to ask the questions like, what might be driving this? And like the first and most obvious is the people in this study on the right have overweight and obesity, and the people on the left have a lean normal body mass index. So obviously, probably body mass index is playing a key role here. And this is the association between body mass index and insulin sensitivity. And you can very clearly see that's a strong association. Perhaps not surprising, but I think maybe the question is, these are similarly aged people who are getting similar levels of sleep, about 5.5 hours. Why are the people who are overweight and obese, like, why are they experiencing seemingly these adverse cardiometabolic effects, whereas the people on the left are seemingly resistant to them, despite the fact that they're all getting what would be considered an insufficient level of sleep? And so is there anything else that might be driving that? And so one thing we've started to look at in these studies is the timing of food intake. We've been trying to capture that with pictures of food. And, admittedly, in the first study, we were kind of just learning how to do that. So the data are probably not quite as rigorous. In the second study, I think the talk study, the circadian study, we're doing a much better job of monitoring people with the pictures of their food. So that being said, we've started to look at just simply as a starting point, the time of their last caloric intake. And we do see in the talk study, which is the participants with overweight and obesity, we see about an hour and a half later on average timing of their last caloric intake. And that's a little bit earlier in the sleep extension study where the participants have a normal body mass index. So that was interesting. I think that's, obviously Andrew McHill here has done some really cool analyses, really looking at clock hour versus circadian timing of last caloric intake and the time of day that people are reaching 50% of calories. And I think we'll be able to do those analyses, at least with this top study where we have dim light melatonin onset and offset. So there's definitely more to be done here. But at this kind of cursory glance with clock hour, we do see this initial difference. And so we looked to see if that was associated with insulin sensitivity. It is. And that is even after controlling for body mass index, this association holds true. And so on the left, that's the normal body mass index participants are in cyan or teal, and then the overweight and obese participants are in the black. And I had one participant, which I'll have to look at this. We have their body mass index, but for some reason in this data set, one participant, their data was missing. And then I also split this out, and I literally just did these yesterday, so I'm happy for any thoughts on these. I split this out between these associations. So this is the same data, but it's actually split out between people with normal BMI and overweight or obese BMI. And the associations still hold true, where later timing of last caloric intake is associated with worse insulin sensitivity. So like I said, there's definitely more to dig into on this, but if it holds true, I think it would be pretty interesting. A lot of the sort of timing of caloric intake data has been related to body mass index. And so if we see that that could also be related to insulin sensitivity, that could be a cool addition to the field. And so with that, I think I've actually pretty much summarized what I want to say. So I will just leave it really quickly. I know I wouldn't have time to get to the shift work stuff, which is perfectly fine. I just want to really quickly thank my lab. It takes a lot of people to run these studies. And then our funding, which is primarily from the NIH. And so if anyone has any more questions, I'll stop sharing and I'm happy to take any more questions.
If anyone has any questions, go ahead and unmute or go ahead and put it in the chat. Or waiting, I have an easy one.
Yeah.
So in your very first slide, you said that OSA is like the second or third best predictor for lower glucose tolerance or insulin sensitivity. How are you screening your individuals with obesity out for sleep apnea?
So we did, so I mean, first we just asked them, like, do you have diagnosed sleep apnea? And if they do, that's exclusionary. And then we do a overnight home test with the Knox device. And basically for that one, we are, if their apnea hypopnea index is 15 or above, it's exclusionary. So some of them could be, certainly in that like 5 to 15 range, which is mild. We could look at, I haven't explored it at all, but we could, so we have a range from, less than 5 to up to that level. We could look at and see if like that's explaining anything in the data as well. But yeah, so that's how we do it with the overnight home test.
It could be interesting to look at because it is such a big thing.
Yeah, definitely.
I wanted to go back to that like brief discussion that you just had with Andrew about the phase angles. And I'm wondering in the lab study where you had the curtailment of sleep opportunity, you had mentioned that there, you don't really know what the light exposure was. So I'm wondering how much of that variation in phase angle that you see is due to melatonin still phase shifting in that study versus it being in some kind of steady state already.
Oh, that's interesting. I could go back and I don't know. That's a really interesting question. Like, because that was a pretty, I mean, we're curtailing it by 2 hours on each side, and we're looking at that. I mean, that's literally on the final day of that. So I think they've really only had like 4 days to potentially shift, which is really not a lot of time. And it's like we weren't very precisely manipulating light exposure. Like if you think about like a phase response curve where like they're in dim light and you're giving them this very precise pulse. So that actually I hadn't thought about that. That's a good question. Like, have they? Is that where they're going to land, or are they still moving someplace?
Yeah.
That's a really good question that I hadn't thought about. I have a different study where it was similar protocol, and we did measure it on the second day, and we hadn't seen much of a shift there. And then we had also measured it on like the 9th day. I'll have to go back and look at that more carefully. I could at least start to answer that question a little bit or give us an idea. That's a really good question. I don't have an answer to it, but it's a really good question.
Thanks.
Yeah.
Maddie, would you like to ask your question? You can. I know we're bumping up, but we'll just do that one and then Dr. Lewis.
Yeah. Hi, Chris. Thanks for the talk. I was just wondering, kind of like what Andrew was talking about with the thinking about like slow wave sleep duration. Wondering if you looked into like the sleep staging at all for your obesity group to see if maybe that's the difference and not total sleep time.
I have not. The obesity group, we do have. So with the data I showed you and our ongoing sleep extension 8-week trial, we're not using the Dream headband anymore. We have the sleep profiler, which I mean, it is what it is. It's basically like a singular electrode on the front of your forehead, but we get 3 nights of data. It works. It's easy for the participants to hook up. So, like the other option would be to go into their home. So like, it is what it is. We can definitely look at it. I haven't, but we will for sure have all that data. And that would also be, that's a really great question. That'd be super interesting because presumably if there are differences there, and we definitely see those differences in Matsuda index, maybe something would come out there. So we'll add that to our paper that we're going to publish in 6 months, and we'll acknowledge you and Andrew.
Perfect. I'll read it then.
Perfect. Maybe I'll look at it. I'll try to look at those data between now and the sleep conference, and talk to me at the sleep conference for those of you who will be there.
All right, really quick. Dr. Louis, do you want to ask your question? Or it's also in the chat, Chris.
Let me.
It just says that. Oh, here's Dr.
Can you hear me? Yeah, there we are.
Oh, yes.
Great talk. So I'll just read my chat. It seemed like some of your Dilmo-Dilmoff changes went counter in direction to the changes in the light-dark cycle, including going back to the first Dilmo-Dilmoff slide you showed. And could we go back to that first slide? It was, I think, your third slide or something.
So you are right. Well, I'm finding it. Some, especially in the free living studies, some of the directional shifts that we see are counter to what I necessarily would have expected to happen. So there's 1 second. I'm getting that. So there's this. This was the first sleep extension one, or are you talking about the one that was in the lab?
I don't remember. Yeah, it wasn't this one.
Okay.
This is a very. By the way, this is a very interesting finding, but it wasn't that. That's not real. That was in the right direction.
Let me. I just want to save this. This one?
No, that's. Yeah, that's the one. Yes. So you've got the lights on much earlier, and you would think that in the 5-hour sleep, and you would think that would dominate the influence of the light dark cycle. You would see an earlier Dilmo with the lights on going from 8 to 6:30 or 7, and you got a delay in the Dilmo.
There also was later light exposure at night as well.
But you would think that wouldn't be as important as the morning light.
The morning light. And there was no shift in the melatonin offset. Yeah, I hear what you're saying. I think I definitely hear that. I guess one thing that the light was, not super controlled in this study from the perspective of, after there was a window in the room after sunset, the participants did have kind of free access to turn the lights on and off. So it's a little bit hard, and that hasn't been quantified. So I can't actually say like what the evening light exposure was, or
they had to keep the lights on, Chris. They had to keep them on until bed.
Okay.
Yeah. It was like it was like $400.
Yeah.
At least.
And so they would have done the same in the morning too.
Yeah. You might expect no shift since there was no change in mid sleep.
I think that's what Ken Wright designed this, but I think like perhaps I don't know if that's one of the maybe reasons that they designed it to have the midpoint of sleep centered was to minimize shifts in circadian timing.
Yeah, I would think so. Yeah. Where is this published somewhere?
The initial finding is 2013.
This figure. Is this figure published somewhere?
Yeah, in 2013 paper from the first author is Rachel Markwald, and it's from the senior authors from Ken Wright's lab. So there's that one, and then there's another paper, 2015 in Current Biology that has the same data as well.
Great.
Yeah.
I'll take a look at them, and we'll take up more of your time here. Great talk.
Cool.
Thanks.
Yeah, Andrew definitely knows what those papers are, and if you can't find them, I can
All
shoot
right.
you
Yeah.
too.
Good.
So,
I might contact them. All right.
Yeah.
All right.
Thank you.
Well, that's we're going over a little bit. I'd like to thank you, Chris, and everyone join me in thanking Chris for a great presentation. And hopefully everyone can get more sleep tonight.